Okay, so we'll go ahead and get started with a couple announcements. So when class ends today, you're going to take your first exam 0. And so that's basically really a logic test. The questions are self-explanatory. You should be able to figure them out. The exam involves a molecule called AZT. There's a couple of introductory slides on that exam that you'll see when we get to the questions. So it's administered through ZipGrade. So you have to go there to log in. You use your USM ID as the first thing, and then the ZipGrade ID is the second thing. The ZipGrade ID is posted in Canvas under your assignment as a comment. There's 30 questions for multiple choice. Each question is worth 2 points. So a total of 60 points. I think when you get to the bottom, there should be a button that says submit. Don't forget to do that. So it's open for 24 hours. There's no time limit, but once you open it, you have that 24 hours. I would caution you on a couple things. Use a laptop or a computer. If you use your tablet or your phone, which I do not recommend, you might not get the screen real estate that you need. The answer key or the form appears on like the left sort of quarter of the screen, and then there's the exam on the right 3/4. And you just click a dot for whatever your response is. So when it closes tomorrow at 12:15, I'll grade it at some point after that, and then you can log into ZipGrade and check your grade. So you'll see your points and then what you got right and wrong on the form. And so those scores are only going to be sort of housed in ZipGrade. Only at the end of the semester will I take all your module exam scores and then move them into Canvas. So at that point, at the end of the semester, I'll take all of your scores, calculate your grade, and basically the way you earn your grade is through points. So if you submitted for the YouTube subscription thing, you got 6 points already. So below those grade buckets, there are the percents of the total grades you have to meet. I don't remember the exact point threshold, but you're going to fill up the F bucket. Then once you do that, you start filling up the D bucket, so on and so forth. And as you can see, the percentages basically, if you do nothing, you're going to get an F. But once you get past 20%, you're in the D. And then, as you see, 40% of the points is a C, 60 is a B, and then 80% is an A. So that's kind of a baked-in 10% curve for the entire course. I would say don't stress out. It's going to be a long semester in some sense, but there'll be other opportunities to earn bonus points. So if you sort of tank an exam, there'll be other means to earn points. So again, I'll explain more of this stuff as we go on. I just don't want to take too much time going through syllabus stuff during the lecture periods. Yeah, the other thing I want to mention, when you do open your browser, try to just sit down and complete the exam within that time frame. So if you go get dinner and you return to your browser like 3 hours later or something, your screen might have refreshed and you lost your answers or something. So that has happened to students. Make sure your internet connection's stable, that when you're taking the exam, you can start it and finish it, all that sort of technical stuff. If you do have issues, to an extent I can help, but I'm really not tech support. The main thing is just making sure your internet's fine and you can log in. Any questions before we get started? Yeah.
How long does it usually take for the full exam?
So the exams really are, I write them as like in-class exams, 60 minutes. So The reason they're online is because I have a lot of students, and if a student can't make it, then they want like a makeup or something, and I don't do that. So you have 24 hours to do it, whether you're sort of in Hattiesburg or not, depending on your situation. But I would say 60 minutes max. It shouldn't take you, longer than that. Obviously, it's online. Once you open ZipGrade, there's no monitoring of that. So it's not like a lockdown browser. I don't see anything. I don't see what you're looking at, where you're navigating to, any of that. I won't say any more about that, but you can sort of use whatever resource you want. I would caution you against posting anything online. I would not do that. But you're free to use your textbook, use your notes, the class notes to help you on these exams. And the character building in that is, what you do now is going to impact how you take the final. So when you're sitting through these exams, you got to make sure that you know the material. Because the final exam is going to be a pretty beefy part of your final letter grade in here. So you want to go into that pretty confident that you can answer these questions, in an efficient manner. Any other questions? Okay, so we're talking about communicating structure in organic chemistry. And for Module 1, we're really just going to lay out what are all the functional groups. A functional group is a specific collection of elements with a bonding pattern, and then all of these functional groups make up molecules. So eventually we'll learn about reactions, how to make molecules, how to identify them using spectroscopy, and then ultimately what are their physical and chemical properties. So the first sort of main set of functional groups are called hydrocarbons. And again, these are compounds with only C and H. This third lecture here, we're only dealing with those bonding patterns. And as we'll see today within the hydrocarbon sort of functional groups, there's specific bonding patterns that carbon can attain. And so based on that, we call the carbon saturated or unsaturated. Saturated means there's only single bonds to carbon. So if we know carbon has 4 bonds, it's only forming 4 sigma bonds. And those are called alkanes. There's a couple types of unsaturated hydrocarbons. So these have pi bonds. So if there's 1 double bond, that's called an alkene. Or if there's 2, that's called an alkyne. And as I said, aromatic compounds, which are more the focus of organic chemistry too, those have a ring. A ring is unsaturated, but it has no pi bond. And we'll talk about unsaturation today, what that term means and how we identify it. But an aromatic compound has a ring and pi bonds. So one of the main things we want to learn, why is organic chemistry important to you? Pretty much everything we use is made up of an organic molecule or has organic molecules in it. So, the human body is composed of organic molecules. At the end of organic chemistry 2, we'll talk about large biomolecules, DNA, RNA, that sort of thing. But really, it's organic chemistry. So in this class, this semester, we want to understand what are the starting materials, where do they come from? So as shown, methane, CH4, that's an alkane. So it's a hydrocarbon that we can get from petroleum, coal, or natural gas. And then we can treat it with reactants and then make something new. And once we do that, we get a product with different properties. And I've given you the melting point and boiling point is just a demonstration of how when you substitute this H in methane for a chlorine, notice the CH3 part, that still stays the same. How does that substitution change the physical properties? So the reactions that we learn, methane's kind of easy because there's 4 hydrogens. But when you get into molecules with a lot of different types of hydrogens, the question is, how do you predict where a reaction is going to occur? And that's kind of where the uniqueness logic part comes in. And then ultimately, how do those functional groups affect the physical properties? So we'll start off by talking about the hydrocarbon functional groups under the concept of degrees of unsaturation. So degrees of unsaturation. And something you'll really want to commit to memory. In the first row of this table where I have alkane, for any n number of carbons starting with 1, the molecular formula for an alkane is CnH2n plus 2. So you just plug an integer in there, like 4. So C4, and then you plug it into 2n plus 2, that's going to get you H10. So C4H10. That has no degrees of unsaturation. Every carbon atom has 4 sigma bonds. So 4 sigma bonds, no pi bonds. For an alkene, now when you look at the molecular formula, what do you notice? It's now CnH2n. So we've removed an equivalent of H2. So H2 is hydrogen gas. So we call it an equivalent. So it's conceptually equivalent to H2. And through that, we're introducing unsaturation. So there's 1 degree of unsaturation because you're missing an equivalent of H2. That means that the carbon atom will have 3 sigma bonds and 1 pi bond to it. For an alkyne, we're now subtracting off 2 more. So we say there's 2 degrees of unsaturation. The carbon atom will have 2 sigma bonds, 2 pi bonds. And the big picture of this so if a carbon atom is a carbon atom, how can it exist in these different functional groups with different bonding patterns? And the later part of today's lecture, we'll talk about atomic orbitals. And you may have been introduced to this concept of hybrid orbitals in general chemistry. The main crux of this issue is that given elemental carbon with its electron configuration, the atomic orbitals do not accurately describe how you can get to these different bonding patterns. So that's where this hybridization comes into play. So again, saturated deals with all 4 of those bonds being sigma bonds. Unsaturated means there's at least 1 pi bond. And then as sort of an asterisk to unsaturation, you can lose a hydrogen equivalent
if you form a ring. And so just to demonstrate that, if I draw 5 carbons, maybe I'll draw 6. So if we have C6, we plug it in there, 6 times 2 is 12, plus 2, that's 14. Now if I bond carbons 1 and 6 together, I'm going to form a new sigma bond. And as a result of that, I have to lose an equivalent of H2. And so that forms a ring. So that's now C6H12. And we say it's unsaturated because it does not have the maximum amount of hydrogens for n number of carbons. But all the bonds are still sigma bonds. Any questions? So I'm going to draw out some structures, and then I'll use, hopefully this doc cam works and I can project some stuff. I'm going to draw just some of these structures, not a whole lot, because the subsequent slides show, N1 through 6 for these different functional groups. So I'm going to put a 1, a 2, a 3, and then alkane, alkene, alkyne. I like to learn stuff by just making tables that can help me condense a lot of information and identify trends, and so that's what we'll create. So we'll call this N. So for C1, we would have H4. Now, you can't have a 1-carbon alkene or alkyne. So that'll become apparent when we fill in the next row here. So for 2 carbons, we would say H3C sigma bond 8CH3. And so that would be ethane. And now with 2 carbons, we're going to remove a molecule of H2 across that carbon-carbon bond. And so this would generate an alkene. So if this is ethane, this becomes ethene. If we took ethene and we removed an equivalent of H2, that would make a triple bond. And this is called ethyne. And so we can just continue the trend here. So CH3, CH2, CH3. This would be propane. And so now we have 3 carbon atoms. It doesn't matter in this structure where we remove the H2 from. You'll get the same thing. So now this is propene. So that the ending of the name, again, is giving you an indication of what the functional group is. And now from that existing double bond where we're going to remove an equivalent of H2, so this is going to be propyne. So this would have 0 degrees of unsaturation. Propene would have 1, and propyne would have 2. So you can visually see that. So in the alkene here, you have this double bond. The double bond consists of a sigma bond plus a pi bond. Then in propyne, you have a sigma bond plus 2 pi bonds. So a degree of unsaturation when you're looking at a structure visually is either a pi bond or a ring. So what I want to point out on these next couple slides, we're looking at the C count from 1 to 6. This is showing you alkanes. And maybe one thing I can point out starting with ethane. See the molecular formula? So all it is it's showing you carbon, then hydrogen. And as we learn more functional groups, any other elements that would be present are listed in alphabetical order. But the convention is carbon, hydrogen, then everything else. C2H6, we can write it this way. And we get to a point, as I said, after 3, you see the carbon count 4. So these have the same molecular formula, but they're not giving you any connectivity information. So those are constitutional isomers, the butane and 2-methylpropane. And once you get up into this issue of constitutional isomers, you can see that as shown in the table, how they're connected will affect their physical properties. And one of the things we'll want to understand in Module 1 is as we learn more functional groups, how are those things going to impact the melting point, the boiling point, solubility in water, that sort of thing. And then the final column here, that uniqueness we talked about, even though the molecular formula is the same, the molecular weight is 58 for both, we can see that the uniqueness is really what is helping us differentiate those two constitutional isomers. So I would say, for lack of a better way of using a term, you do want to memorize the names for the carbon counts 1 through 10. Not necessarily any constitutional isomers of them, but just the linear ones. So what are their sort of parent names? Methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. Again, once you get past 5, the prefix of the name is a number, and that tells you the carbon count. So those are alkanes. These are now alkenes. There's no C1 alkene. You have to have at least 2 carbons. Once we get past 3, notice with 4, there are 3 constitutional isomers of C4H8. And these have, if you look at the names, 1-butene, cis 2-butene, trans 2-butene. So these have some other information in there that helps differentiate them. So 1-butene. The but tells you there's 4 carbons. The ene tells you there's a pi bond. The 1 tells you where the pi bond starts. So I have 4 carbons. At position 1, there's a pi bond. So now we have two butenes, but then there's these other words in front of them, cis and trans. Cis means same. Trans means opposite. What is that related to? So I'm going to draw trans 2-butene. So I have 4 carbon atoms. The 2 is telling us the pi bond starts at carbon 2. Now what does the trans mean? If you look at just the pi bond between carbons 2 and 3, each of those has a CH3 group and then an H. Let me draw cis 2-butene. So notice in the trans 2-butene, the methyl groups at carbons 1 and 4 are opposite to one another. Then in cis 2-butene, they're on the same side of the pi bond. So cis and trans are related to pi bonds, and how those substituents are organized relative to one another. We'll talk more about nomenclature later on, but as you go through and you review these, what you can practice is, given that name, can you actually draw the structure? And then once you've drawn the structure, can you go over to the final column here and verify that the uniqueness is correct? So the hydrocarbon with 2 degrees of unsaturation is called an alkyne. And so this means there's a triple bond. And again, once we get past 3, now we have these 2 constitutional isomers. So for butyne, there's 1 butyne and 2 butyne. So the but says there's 4 carbons, the ine says there is a triple bond, and the 1 says the triple bond starts at carbon 1. So 2-butyne, now the triple bond starts at carbon 2. Any questions? Yes.
Did you say on represented?
So YNE is a triple bond, and those are the alkynes. So alkanes, alkenes, alkynes. So these are 3 of the, say, 15 to 18 functional groups that we'll learn in this module. Once we start using other elements of the periodic table, we'll start bonding those to hydrogen or carbon. Those make different functional groups. So for the carbon-carbon bond shown, what suffix should be used in naming them? So we have a sigma bond, sigma plus pi, sigma plus pi plus pi. So the sigma bond is an alkane, so we can eliminate B and D. Sigma plus pi, that double bond, that's an alkene, so we can eliminate A. And then that's going to leave us C. So alkane, alkene, alkyne. So that's what you're looking for in how you would identify what hydrocarbon functional group is present. So here's a table of those functional groups. Probably the main difference now is the second column in there says cycloalkanes. And again, those are rings. When you have a chain and you tie it back to itself. So for 2 carbons, the alkane is ethane, the alkene is ethene, and the alkyne is ethyne. For 3 carbons, we have propane. And now 3 is the minimum number of atoms you need to form a ring. So 1, 2, 3. If we take carbons 1 and 3, bond them together, we can make a ring. And then we put this word cyclo in front of it, so cyclopropane. The alkene would be prop 1-ene. I learned it this way, 1-propene. Again, that number tells you where the double bond starts. You can do it that way as well. Just shove it into the middle of the name. And 1-propyne. So once we get up to 4 carbons, now we have what I'm calling linear versus branched. So let's walk through these. So a 4-carbon alkane is called butane. If it's in a ring, it's cyclobutane. For the alkenes, we have 3 constitutional isomers, and that depends on where the double bond is starting, as well as the location of the substituents. So 1-butene, trans 2-butene, and cis 2-butene. This E and Z, again, the first couple modules we're not concerned about nomenclature, so I'm not going to go too much into that right now. One of the maybe frustrating things about this class is there's always a way of doing something, and then there's these other sort of shortcut ways, and they sort of get merged. So cis, trans, E, and Z describe the same things, and they're all commonly used. The alkynes, we have 1-butyne and 2-butyne. So for the branched isomers, now we've reduced the longest chain and we're making these substituents. So for C4, we have 2-methylpropane. For the ring, we have methyl cyclopropane. And then for the alkene, 2-methyl-1-propene. For the alkynes, there's no branched ones. Any questions? So if you had 7 carbon atoms, and you wanted to figure out how many hydrogens were present for an alkane, an alkene, and alkyne, you would use those formulas. So if we plug 7 into the alkane, we would get 14 plus 2. That gets us 16. So again, this is a canned sort of question. Once you figure one out, you can eliminate the distractor answers. So A, B, and D are all out. And then C would be right. So for the alkene, 2 times 7 is 14. In the alkyne, 2 times 7, 14 minus 2, that gets you 12. So it says, is the molecular formula C8H18 fully saturated? So N equals 8. So by this we mean, is that molecular formula an alkane? So if we plug that 8 in there, we would end up with C8H16 plus 2, that's C8H18, so yes, that's fully saturated. And let me just explicitly mention this, because I said when we get above carbon count 4, for any molecular formula, you're now going to have multiple constitutional isomers. So this is explicitly telling you that formula is an alkane. So if you were to figure out what are all the possible constitutional isomers, at no point should you draw an alkene or an alkyne, because then you're not going to obey that molecular formula. So for the 3 C8 hydrocarbons with the names shown, octane, 1-octene, 1-octyne, how many double bonds should each have? So an alkane will have none. So A and D are out. An alkene should have 1, so C is out. B is the correct answer because 1-octyne should have 2 double bonds. Any questions? So now, how are we going to use that degree of unsaturation concept? So we're basing this problem solving in the fully saturated molecular formula. So we really want to keep that always present in our mind, CnH2n plus 2. So when I give you some random molecular formula for n number of carbons, you want to see what is the maximum number of hydrogens that n should have. Then if it does have a degree of unsaturation, that's informing you of what are the possibilities for that molecular formula in terms of drawing constitutional isomers. So if we were given C4H6, so N is 4, what is the maximum number of hydrogens for 4 carbon atoms. So when we plug that 4 in there, 2 times 4 is 8 plus 2, that gets us 10. So for 4 carbon atoms, the maximum number of hydrogen atoms is 10. So C4H10. And this is, someone asked about math in the Monday lecture. This is sort of the extent of organic math right here. So what are we given? C4H6. The carbons always cancel out because the N is the same. So H10 minus H6, that's H4. And 1 degree of unsaturation is defined as H2. Because remember when we were going from an alkane to an alkene, and we stripped out an equivalent of H2. So we're going to take our H4, divide by H2, and that's going to give us 2 degrees of unsaturation. So now I said a degree of unsaturation is equivalent to H2, but structurally speaking, what is that? It can be a pi bond, or it can be a ring. Any questions before we move on?
Wait, how do you know if it's like a bond ring?
So that'll be on the next couple slides.
Oh,
So let's put that into practice, and then we're going to go over that C4H6 in relation to that question. You're given C10H12. So when we plug that 10 into the alkane formula, we get C10H22. So we just subtract the numbers. That gets us 10. We divide by an equivalent of H2. So that gets us 5 degrees of unsaturation. So this says, is C6H16 a reasonable molecular formula? What do you think? See some heads shaking. So no. So why not? So there's too many hydrogens. The maximum number of hydrogens you can have for 6 carbons would be 14. So again, chemically speaking, the reason you can't have 16 hydrogens, because you're going to get to a point where every carbon is saturated with 4 bonds, and then you're going to have to stick 2 more hydrogens in there. And unless you're looking to win a Nobel Prize, ain't going to happen, because carbon is not going to accept any more bonds than 4. So the point of this exercise is if you're given a molecular formula, can you propose reasonable structures? To put that in a lawyer sense, you're proposing something which is a claim. And how do you provide evidence to your claim to increase the confidence that this constitutional isomer is correct and it's not this one, even though they have the same molecular formula? So the reason that's important, I assume everyone in here has seen a physician at some point in their life. One of the reasons you go to a doctor is to get a prescription for something. It's like, I have a migraine, I need a pill to help it go away. So that pill is a drug. It has a very specific structure. The active ingredient in that pill is that structure. It's not a constitutional isomer of that structure. So for that pill to be prescribed by a physician, it has to go through an approval process by the Food and Drug Administration. And the companies that make it have to prove without a doubt it is that structure and not something else. So when you're considering a molecular formula and you have 5 degrees of unsaturation, is what you're claiming the structure to be, is it that? Does the data, the uniqueness set match that? If it doesn't match that, then what you're claiming is not correct. If a patient gets that prescription and they develop a symptom, then that's a lawsuit, that's a lot of money. So the implications of this are pretty broad. So you can be reasonably confident that anytime you do get a drug prescribed to you by a physician, not your next door neighbor who you might be getting other things from, but through CVS or whatever, it is that structure and it's going to act upon what it's prescribed for. So the game here is, once you find the degrees of unsaturation, what are the possible combinations of functional groups that you can come up with to draw constitutional isomers? So how do you logically find them? And once you do find them, how do you differentiate them? That's the uniqueness part. And then, once you find those claims, you can go to the internet and look at databases to see what their physical properties are. That will also differentiate them. So there was a question about, this molecular formula said there was 2 degrees of unsaturation. How do you know what they are? Because we said for any 1 degree of unsaturation, it can be either a pi bond or a ring. So if you have 2 degrees of unsaturation, you have 3 possibilities. The first one is you have 2 pi bonds. The second, you have a pi bond in a ring. Or the third, they're both rings. And let me tell you, as you increase n in that formula, the number of constitutional isomers you can draw is not a small number. When you get up to like 5 and 6 carbon counts, I'm talking you can draw about 50 different structures. So I'll draw some of these. We're not going to draw all of them because we want to get on to other things, but I'll give you a taste of what we're doing here. So we have 4 carbons and we want to draw 2 pi bonds. And so we can either draw 2 alkenes for that, or we can draw 1 alkyne. So there's 4 carbons. That would be 2 pi bonds. So that would be an alkene. If I wanted to draw an alkyne, so for 4 carbons, if I wanted to do the second column that has a pi bond in a ring, so I would draw a ring. So that would be cyclobutane. But now I need to put a pi bond in there. So this would be cyclobutene, ENE. And with 4 carbons, can I draw a structure that has 2 rings? So I'd have to go, there's 1 ring, and there's another ring. And then I'll let you use your imagination. Anyone see the old Willy Wonka movie, Charlie and the Chocolate Factory, like the old one, not the Johnny Depp weird one? You know, at the beginning, there's a song in there about using your imagination. And so I think to develop the logic to really understand this material, from that one molecular formula, if you understand how this table is laid out and you understand Lewis dot structures, you can come up with a lot of constitutional isomers. And your mental check in that is making sure you're not violating the Lewis dot rules. But then you're also following, like in column 1, pi bond, pi bond. Column 2, pi bond ring. Column 3, ring, ring. So once you propose something that's your claim, just make sure you're not violating a rule. And then with these existing structures, you can figure out the carbon uniqueness, the hydrogen uniqueness, and you'll see that for the most part, they'll all be different. So here are some of those structures. We'll calibrate. So we'll calibrate and see if we understand the logic. It says, which of the following is not a viable constitutional isomer of the molecular formula C4H6? So we said B. Why is that? So it has C5. So that's, again, the kind of stuff you're looking for is that check. Is the number of carbons right? Is the number of hydrogens right? If it's asking for a specific functional group, does that structure show it or not? Which of the following is an alkyne constitutional isomer of C4H6? So C, so the triple bond, that's the alkyne. Which one has the uniqueness set of two unique carbons, two sets of hydrogen, and then the ratio of 4 to 2. Someone say D. So it can be either A or D. So in that case, since they have the same uniqueness with the same molecular formula, ultimately, if you were to increase your confidence towards one or the other, you'd have to look at the specific data. And that's going to help us. I don't know the exact slide order, what's coming up next, but if you look at the carbons in A, see how they're all sigma bonds, but in D you have pi bonds? The nature of how those carbons differ affects how the actual data looks. And so we'll explain that logic a little bit now, but also as we progress through the semester.
With that, like, where is the second set?
Which set do you see so that I know what, where are they?
In the middle.
So if we draw the hydrogens out, remember for carbon, we're not explicitly showing H's. So if we draw them out, H, 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 and then H, and H.
Okay. So that's two identicals. Since they're identical, it counts as one. That's 1, 2, 3.
So this is a set.
Okay.
That's the 4. And then these are a second set. That's the 2.
Okay. Oh, okay. Thank you.
So again, one thing that this class will definitely challenge you on, I'm drawing this stuff flat, as we'll see in a couple minutes. The molecules are not flat. And I think you might have purchased a model kit for your lab. You should definitely use that model kit. Since these things exist in 3D, one of the things that can be hard to spot are the symmetry elements. So that molecule A has a couple different symmetry elements. There's a horizontal one, and then there's a vertical one. So you have to get used to thinking about things, you're looking at it one way, but can you rotate it and think of it another way? The model kits will help you. If you have that visual skill, it will definitely help you as well. Questions?
Wait, so for the second hydrogen with like A,
So the last 15 minutes here, the crux of the issue now, to explicitly state it, is we know from the periodic table that carbon lies in a certain spot on the periodic table. As we'll see, it has 6 total electrons. If a carbon atom is a carbon atom, why can it exist in these different bonding patterns for an alkane, an alkene, and alkyne? What allows for it to form a double bond versus a triple bond if the total electron count is staying the same for carbon? So to understand this, these are the two types of atomic orbitals we need to remember. So S and P. So the S orbital was spherical shaped. And then the p orbitals are dumbbell shaped. Notice that for the p orbitals, there's 3 of them. And what differentiates them is the axis upon which they lie in 3D. So is y, x, or z reading left to right there. So those are atomic orbitals where the electrons in carbon reside. So carbon is element atomic number 6 on the periodic table. It has 6 total electrons. We're not going to talk too much about filling atomic orbitals. You know, as you increase, you're adding 1 electron, then they start filling these orbitals. So it's 1s2, 2s2, 2p2. The 1s2 are called the core electrons. The 2s2, 2p2 are called the valence electrons. The core electrons are not used in bonding. The valence electrons are used. And as you see in this, visualizing these, there's the 1s, and now we're in the second period, 2s, 2py, 2px, 2pz. So 1s2, 2s2, those electrons are paired. Now when we get to the p orbitals, there's 3 of them, but there's only 2 electrons. So they go in unpaired to begin with, right? Now the crux of this issue is for the 2s2 and 2p2, the 2s2 are already paired. If they're paired, how can they be shared in bonding? The 2p1s that fill the y and x orbitals, they're unpaired. So they can form bonds. But then the issue is, look at how they're oriented. They're 90 degrees to one another. They're on different axes. Going from an alkane to an alkene to an alkyne, the carbons are going to have different shapes because they're bonded. They have 4 total bonds, but they're in different patterns. In the last figure on the left there, this is probably the best representation of atomic orbitals. You see how everything's like overlapped? The reason this is sort of not good is because it gives you this idea that everything's separated. So the 1s orbital is that little blue ball. The 2s orbital is like that green ball, which is encapsulating the blue ball. The 3s, which we're not talking about, is even bigger, encapsulating it all. And then you have the p orbitals, and they're lying on these different planes. So the atomic orbitals do not accurately describe what we see in these functional groups. So there's not a good explanation for alignment in how carbon looks in an alkane versus an alkene versus an alkyne. And, you know, this all gets back to, you know, the late 1800s, early 1900s, when through the discovery of nuclear radiation and people started thinking more on the atomic scale in quantum physics that, okay, we know from, remember in Gen Chem, those light transitions, the different elements showed these different line spectra. So we know that that corresponds to atomic orbitals, but atomic orbitals don't accurately describe what we're seeing in molecules. And so the physicists and mathematicians thought about this more and basically said something else has to be happening, because we need to account for how these electrons, the valence electrons, can be used in the different bonding patterns. So the fallout of all of this is that the s and the p orbitals have to be mixed. And the word we use is basically they hybridize. And all of this is rooted in mathematics, which is, again, beyond the scope of this course. We're just qualitatively concerned. How do we make sense of this? What are the shapes of those hybrid orbitals? And on the left here, this is atomic carbon. There's our electron configuration. So we have 6 electrons. We start filling it from the 1s. We pair it. The third one goes into the 2s. We pair that. The last 2 go into the X, Y, and Z. So those are the same energies. They're called degenerate. So they're the same energy, they're on the same level. Again, the reason you don't initially pair it is because it has to go into an unoccupied orbital first to maintain the energy level. And so what these brilliant people did through the mathematical equations was say, okay, we're basically going to take, there's one s orbital in period 2. Then there's 3 p orbitals in period 2. So we're going to take them and mix them together mathematically. So that's the hybridization. If we take all 4 of them, the s, px, py, pz, we get 4 sp3 hybrid orbitals. And their energy level lies somewhere in between the s and the p energies of the atomic orbitals. But notice that they're all on the same level. So this level right here is what I'm talking about. And now we can take the individual electrons and stick them in one in each orbital, and that will allow us to form 4 bonds to carbon. But how do then we explain an alkene which has sigma and pi bonds? Well, we're going to take the s orbital and only 2 of the p orbitals and make an sp2 hybrid orbital. So there's 3 of them. And then we're going to leave 1 p orbital at the same energy. And so this line right here, that double bond, really what that means is there's a p orbital with an electron, a p orbital with an electron. 2 electrons make a bond. They form the pi bond. And then for the alkynes, we're going to take 1 s and 1 p. To make sp hybrid orbitals, we leave 2 of the p alone, and that allows us to form 2 pi bonds. So maybe if this getup works, maybe not. You hear me pressing that, right? Okay. Let's think about it. Okay, there it is. I did cut my fingernails. So that is an alkane. So the black atoms are carbon, the gray lobes are sp3 hybrid orbitals, and then the white atoms are hydrogen. So notice that the carbons have 4 sigma bonds. And as you can see, when I move this around, because of those 4 things bonded to carbon, they're projected out differently than you would see in atomic orbitals. So they're on different planes. So that necessitates that we use different words to describe. So an sp3 hybridized carbon is called tetrahedral. So if we remove 2 hydrogens, we're now going to make that, where each carbon atom now has 1, 2, 3 sigma bonds. And then it has this purple and pink. The thing in the middle is the connection between the 2. So overall, that's the pi bond. So even though on the structure we're just drawing a second line to show the pi bond, because of that dumbbell shape, the electrons exist above and below the sigma bond. And now that carbon atom, it's no longer tetrahedral, it's called trigonal planar. So you have 1, 2, 3 atoms trigonal. And if you look at sort of that way, they all lie in one plane. And then for the alkyne, it's a better way to look at this. So what I'm holding now is 1 pi bond, and then 90 degrees to that is the other pi bond. So you have a sigma bond plus a sigma bond, pi bond plus a pi bond. And so that, if you look at those 4 elements, H, C, C, H, that geometry is now called linear. So structurally, when you're looking at alkanes versus alkenes versus alkynes, just by the counting, if there's 4 sigma bonds, it's sp3 hybridized and it's tetrahedral. If there's 3 sigma bonds plus a pi bond, it's sp2 hybridized, it's trigonal planar. 2 sigma bonds, 2 pi bonds, it's sp hybridized and it's linear. So I know we're about out of time, but we got about a minute left. These are just pictures ripped out of your textbook that show that. And what I want, there's the pictures. I want to show you before you leave. We'll sort of pick this back up next week, but there's 3 videos linked to an external channel on YouTube, and the company is called Spanholz. So they made these videos. They're a little bit weird, but I think they're nice because the animations show you how this hybridization happens, how you get these different bonding patterns in the hydrocarbons, and then ultimately what the shapes are. So if you're still a little murky on this, you can invest some time in watching those. Again, they're linked through Canvas. But your exam's going to open up. Take a look at it. Whenever you have time, sit down, complete it. If you have issues, send me an email. I'll try to respond within a reasonable amount of time. But then we'll see you next week on Monday, where we're going to start introducing other elements into these bonding patterns.